Раз.
Okay, so today we're going to start second chapter of this course. So limits and co-limits to dual notions, and we're going to start with the notion of the limits, but we're going to go from the easy examples to the most general definition. So we start with the products. This is our first example of the limit constructions. So products in a category. Definition is quite simple. We have two objects, so four objects x and y in some category C. A product is a triple. So the first is an object in the category, or just the product of x and y, and then we have two projections. So let me call this P1 and P2. So this is a triple. So, well, I want to say that sometimes people a little bit abuse notation and say just the product is an object and kind of forget about these two projections. So P1, P2 are called projections. But to do proper theory, we need all the information. Well, and then we need to formulate the so-called condition that making this object universal. So it says the following: if you have this product, these two projections, P1 to the x, P2 to the y, and now suppose you have any other object, say f, and suppose you have maps, say f1 to the x and f2 to the y. So this is kind of data more or less the same that we have here. It's an object and two maps, the x and to the y. So then, for this situation, there is unique map. Oh, let's call this temporarily maybe h. So there is unique map h from f to the product, such that these two triangles are commutative. So that's a formal definition of a product. Well, we can look at this a little bit differently. So product is a terminal object in the following category. So for objects in this category, we have triples, say f and two projections. So these are triples, and f1 is a map from f to the x, and f2 is a map from f to the y. And maps, well, say I have map phi from the f. Well, okay, so f, f1, f2, and then I have g, g1, g2. So what would be a map for? It is. But we're going to do this, we're going to see this at the very end of the lecture. So everything is an example of a common category. That's correct. So here, what's the map? Well, it's quite naively, just, well, here you have f1, f2, f1, f2, x, y. Here I have g, y. Well, maybe even better if I just use the same x and y, maybe. So it still maps here, so g1 and g2. Now first the map is just a map from f to g, such that these both triangles are commutative. Okay, so we see that with this definition of a category, this is exactly means that the product is a terminal object, right? Just a formulation. But this allows us to say immediately that product is unique up to unique isomorphism. Okay, so I have several remarks. First remark is that you have a natural isomorphism induced by the projections for any object T. Right? If you have element here, these are two maps, and from these two maps, say, well, actually before I was using not T but F, so let me change this to the F as before. So here we have F1 and F2, we can uniquely construct a map here. And if we have map here, compose these two projections, we get elements here. So this is not just some random isomorphism, this isomorphism that is induced by the composition with these two projections. Yeah, and there was a temporary notation for the H. Actually, for this unique map, there is a standard notation. Usually people write something like F1 and F2 in chevrons. Okay, this is, well, with this formula you can think about the product in a different way. You take these two representable functors, you take a product in the sets, and ask, is it true that this functor on the right-hand side is representable? Or it's exactly representable by the product of two objects? Well, if it exists, of course. So, remark 2. Suppose I have a terminal object. Do you see what's the product of a terminal object and any object? So this is isomorphic to X, and of course in the other order this is still true. Right, we just need to check the definition. So here I have, well, I want to say that this diagram is a product. Remember, product is an object with two projections. So this projection is kind of canonical because it's a terminal object, and this is the identity on X. Now, if I have any other object, say F, well, here I can choose anything. This is map to the terminal object, and here this is maybe some map F. Or if I want to show that this is that X is a product, I need to say that there is a unique map from F to X such that this triangle is commutative. So this is, see it here. C is any category. We have category C. We took two objects X and Y. In this, and here actually we have category and with the terminal object. And of course, the only map that we can put here because it's the identity is map F itself. And the same works for the second isomorphism. Okay, some other remarks, maybe 3. Well, what map? Here? This is terminal object. There is a unique map from any F to T. So the product can be generalized this triangle because there is only one map. So if you compose pre-compose this one map with any map, this is still the only one map that there is. No, this is because no matter what you're trying to do here, the map is still the same map that is here because there is only one map. Okay, so the product can be generalized to any set of objects. So clearly, if you have two objects, you have this definition, you can do the same for any set of objects. So then you'll get something like this. You'll get a product of objects with canonical projections. So here, phi I is the map from the product to the xi. And little I is in some set I. We just repeat everything. There is universality property, there is a corresponding category, it will be terminal object, and so it's unique up to unique isomorphism. So let's do examples. Sets. So what's the product in sets? For example, for two objects. Yeah. So this is just the ordinary ordered pairs. Notice, by the way, this is a little bit different than the usual set construction. It is not unique in the category of sets, only unique up to isomorphism. If you just have access to the set theory, it is not possible to form a product. Of course, it is possible, but there are too many choices. There is no canonical choice for the product. Okay. Well, if you try to consider algebraic versions of this, the answer is still the same. So if you take monoids, groups, rings, then yeah. So how you define ordered pairs in the category of if you just know set theory? Different people can come up with different answers. The answers will be isomorphic, but the answer is not canonical. Yeah, so for the monoids, groups, and rings, well, everything works just fine. You take two monoids, take a product in the category of sets, and then there is a product subcomponent-wise. The same for groups, the same for rings. This is what we usually use in the first semester of algebra. And also notice that sets have not just binary products, but all products. Right? For any set of sets, you have a product. And the same for monoids, groups, and rings. And if you consider, for example, topological categories, again, all products exist. Now, well, an interesting example is the category of metric spaces. What metric spaces I want to take? Well, I think Lipschitz will be fine. Что утверждение? Просто что называется произведение. If you have any family of topological spaces, you have a product topology. Right? So you have open sets in okay. You take a product like this for opens, right? And then almost all of them are equal to the space. So except finally many. I think that's the standard definition of a product topology. Okay, for the metric spaces. So let's take two metric spaces to begin with. So we have one and the other. Okay, can you tell me what metric I'm supposed to put on the product? Yeah, so essentially you can do the following. I prepared. Dun, dun, dun. Yeah, so here you're going to put metric then depends on the n, and n in this case is just any norm on R2. So this is norm. So in a sense that if you want to compute this dn x cross y on, say, x1, y1, x2, y2, then you compute the distance in the space x for the components x1 and x2, compute the distance in the space y between y1 and y2. This will be just two real numbers, and then you can compute norm of this thing as a vector. So you can see, of course, all norms are equivalent, but kind of there are many different norms. So, you mean there are more possibilities for this thing? Sure. Yeah, I'm just giving you kind of a family of examples that works. So in this case, the product, we can see that is highly non-canonical. There is no canonical choice for this structure. That's the point of this example. Of course. Well, this is metric spaces with Lipschitz maps. Maps in this category are Lipschitz maps. Well, I think this still works for continuous maps. What I think won't work is the following. What would be a product, now say, of a countable family of metric spaces? Yeah, but is it true that this metric gives you a topology, which is a product topology? I don't think that this is correct. So I want to say that this works fine, for example, if every space xi has a finite diameter, and these diameters are universally or uniformly bounded by some constant. Then that everything is fine. Other than that, I'm not sure that this is a reasonable object to study. So here, I think this is an example where you have binary products. Of course, if you have binary products, you have all finite products. But for infinite products, you have some problems. Well, I think this doesn't exist, but okay. Maybe let's put aside this example with metric spaces. What would be a nice algebraic example when you have finite products, but no infinite products? sure, why not? All objects are finite groups, and maps are group homomorphisms. Yeah, so examples like finite dimensional vector spaces, maybe finite abelian groups, and I think even just finite groups, right? They all have finite products. But no, say, countable. Okay. Yeah, and maybe the last example that we already discussed in the first lectures, the category of all categories, maybe this or this. I don't know such examples. But I think it's not possible, to be honest. Okay. Now I want to fix some notation. This is the category of categories. So here we also have products. So this is category for small categories, and this category of all reasonable categories. And both of them have products. Okay, so I want to give a definition of the diagonal map. Diagonal map. So if you have at least binary products, you have canonically a map, which is usually called delta. Sometimes it is called delta x. This is the canonical product from the x to the product of x. Of course, for sets it will be really the diagonal map. But you can define this abstractly. Well, since you have product to projections, and the map from x to the product by the definition of the product is completely determined by these two maps. And here we have 1x, 1x. So the map here is delta. So categorical definition of the diagonal. And yeah, so next definition. Next definition tells us that product is a factor. So suppose I have two maps, f from x to x prime and map g from y to y prime. So let me start with the product of x prime and y prime. We have two projections. Now I have x. From x there is a map f. Y from y there is map g. And here I have a product. Again, two projections. Now I can look at these compositions. This will be a map from the product of x and y to the x prime. So this composition and this composition. But then by the definition of this product, there is a unique map here. By the way, if you start with some diagram and then you can show that there is a unique map, you usually use dashed arrows in this case. So this unique map is by definition f product with g. So the product is not only defined on objects, also defined on the maps, so this is a factor. And there is a relation. If I take two maps in braces, this is the same thing as the product of two maps composition with the delta. Now again, for proof we need to look at a couple of commutative diagrams. So I have x, which is mapped by the diagonal map to the product. Here there are projections. These maps are the identity maps. Here there is a map F product with G, Y product with Y, again projections to the Y, and this is F, this is G. So, of course, everything is commutative. And then we have another diagram, Y product with Y, two projections to the Y, and now here what was it? This is product. This is what we get in the product diagram. This is X and this is Y. Okay, so here we have this composition on the right hand side. Now I need the diagram with the, so this is Y, this is Y, so hence I have X. Here I have map F, here I have map G, hence there is a unique map here, which is the F and G in chevrons. Right. So I think everything is fine. Now, this is a terminal object, so the map is unique, so it has to be inside. No, otherwise you won't get this formula. You want, for example, you want to, for example, put primes here. Okay. Yeah. But we're going to use this formula later, so I wanted to prove this separately, because the proof is very simple. And when we're going to use it, we're going to use it in this context. Y is the same as Y prime. But of course you can generalize this. Okay, that was our first example of a limit. Now let's go to the second example. Equalizer. So here, equalizer. Let me for shortness just write EQ for equalizer. So of two maps. So I have X and Y objects and two maps F and G. So is an object, well, actually, again, object and projection, so is a pair. Let me say pair of an object and a map. And notation for this is EQ of the pair F and G. So what's the definition? So here projection is a map to the X such that this map E kind of equalizes F and G. In formulas, it means that if I take F, recompose this with E, I get the same as G. Of course, we need to formulate a universal property in this case. So this is a pair with one object, as before, object is always one, with a projection to the data, and we need a universal property, meaning that if I take another object, say Z, this here will be map H, so for any pair Z and H. Of course, as before, I need to assume that this property is satisfied, meaning that FH is the same as GH. And this implies that there is a unique map, say U, from Z to E, such that this triangle is commutative. That's the definition of an equalizer. Do you know any equalizers from your algebra courses? So if it makes sense to take a difference between two maps, f minus g, for example, for abelian groups, modules, then the equalizer is exactly the kernel. Again, as before, we can notice that an equalizer is a terminal object in some category. I think it's clear what's the categories and what are maps in this category. So objects are just these forks, right? And maps are maps between forks that make this triangle commutative. Okay, remarks? If C has a zero object, remember that the zero object is initial and terminal at the same time. Then we have a notion of a zero map, which is say, zero object Z, which is a map that factors through the zero object. Then we can introduce notion of a kernel of a map. So by definition, kernel of some map F will be equalizer of the map F and the zero map. So here, this is F is a map from X to the Y. So to define the kernel of a map, we need, well, this is exactly the point. In general, in any category, you can only define equalizers for two maps. But if you have a notion of a zero map, well, you can introduce notion of a kernel. You need additional data to do this. Okay, second remark is that we can again generalize equalizers to any set of maps. So namely, we can introduce equalizer, and here we have a family of maps Fi parameterized by some set. With the same definitions and the same universal property. Examples. Let's start as before with the category sets. So what's equalizer of the two maps in the category of sets? And you can check easily that if we just use this and plug in into the formal definition, then any map of any set Z with any map H actually factors, well, it actually maps element from here to X to the equalizer. So in fact, it's for any element you take the image. In fact, it's not in X; it's actually in the equalizer defined in this way. There is no surprises here. Now, for algebraic categories like monoids, groups, rings, everything works fine, right? Because when you look at this condition, so you need to check, for example, this is closed undertaking products. Definitely it is. This is closed undertaking sums. Again, it is. If you have something called rings. So these categories, say this is star works. 3. In the topological categories, also there are no problems. Again, everything works. Now, as a special case, when you have something like R modules, maybe some special cases, vector spaces, abelian groups, and then here we have a nice formula that equalizer of an F and G is the same thing as the kernel of F minus G. About equalizers, I have two simple observations, which take longer time to formulate than to prove. Proposition: in any equalizer, E is mono. So let's go back to the definition. Equalizer gives us this diagram, which is usually called the fork diagram, F, G, Y. Okay, so I want to... Yeah, so E is the part of this data, so this map. I just don't want to write a lot of words. So E is from the equalizer, the projection from the equalizer. So I want to check that this is a monomorphism in the category. Well, I start with some test object Z. Suppose I have two maps, Z1 and Z2. So I know that I have E Z1 is equal to the E Z2. And I want to check that Z1 is equal to Z2. Right? That's what means that this is mono. Right? So I want to show somehow Z1 is equal to Z2. Well, if you just look at this composition, which is E Z1, E Z2, the same thing, right? So that's a commutative triangle. But for any Z to the equalizer, there is only one map, such that this is a commutative triangle. Hence, we prove that statement. Agree? We start with two maps. We know that two compositions are the same, so this is what I have here. So meaning that I have map from Z to the X equalizing F and G, because E is equalizing F and G. But if Z is equalizing F and G, there is a unique map from the Z to the E. And here we have two maps, they have to coincide. Next proposition. And by the way, let me add this as a remark. Such mona are called regular mona. So regular mona is by definition projection for some equalizer. Of course, it's a very special kind of mona. Not every mona is of this kind. For example, actually, let's formulate the next proposition. So the following conditions are equivalent. So first, we still study the same situation with the fork. So F is equal to the G, two maps coincide. 2, the projection in the equalizer map is the identity on X. 3, E is an isomorphism. 4, E is an epimorphism. Proof? Clear. It doesn't really require any proof. Do you agree with me? Now, if two maps coincide, is it true that identity equalizing two maps? Of course. Now, if this identity is clearly an isomorphism, if it's an isomorphism, it's an epimorphism. Now, if it is an epimorphism, F coincides with G by the definition of the epimorphism. So, for example, we can say that if we have a map which is regular monomorphism and epimorphism, this is an isomorphism. Next class of limits, full maps. Definition: a pullback of a diagram of a very specific form. So here in the diagram we have X, Z, and Y objects and two maps, F and G. So F from X to Z, G is from Y to Z. So I guess now you can see a general pattern. If you want to define some limiting construction, you start with some diagram. For objects, it's just two objects. For equalizers, two objects and two maps going in the same direction. For pullbacks, you start with this diagram, three objects, two maps. Then you define kind of new data for this diagram. So something with projections. So pullback of a diagram is again a triple. You have object, standard notation is this, product over Z with two projections, P1 and P2. So what it is? Well, we have, let me draw this a little bit differently. This is a standard way how usually people draw this. They draw this as a square. So let's deform this diagram into this part, and then product, which is a pullback, is the next part of the diagram. So I'm going to call this P1 and this is P2. So take some diagram and then define the limiting construction as object and projections. So here we have object and projections. Well, it has to satisfy some universal condition, so such that for any other triangle like this, say F, here this is F1, this is F2, X, well, I already have F, so it's not very good. Maybe let me call this T, T1, T2, Y, G, F, Z. So pullback has a universal property. If you have any other commutative square, there is a unique map. So let me repeat this. X product, pullback over Z, projections, Y, X, Z, G. Now I have some other object T and maps. This is T1, this is T2, and then there is a unique U, such that these two triangles are commutative. Okay, so pullback is a terminal object in some category. So do you see what the category is? Now the category are exactly this data, an object with two maps, such that this square is commutative. And of course the maps are just maps between objects, such that the corresponding triangles are commutative, exactly like in this picture. So that will be a map, and of course by definition of a terminal object, we see that this is a pullback. Okay. Remarks as before. Well, first of all, there's a remark about notation and terminology. Pullbacks are also called fiber products. And there are also different notation for them. So the notation that I use is also can be written in this form, product over Z. And sometimes, in some situations, object Z is not enough for the notation. Yeah, fiber product. Расслойное произведение. Pullback, расслойное произведение. Еще говорят Декарт в квадрат. Well, I was saying that sometimes it's from this formula, it's not clear what are the maps. So in some cases, Z is fixed, and you need to study different maps F and G. So people also invented notation where you put F and G around the cross, say, just just another notation. So remark 2, pullbacks are products in the slice category. That's another way to interpret this. 3 products in 3. So let's take a terminal object. So that was a category. Objects are all diagrams like this. C is an object in C, and there is a map to some fixed object Z. So objects over some object. Like in geometry, you used to have some families of varieties or given varieties, like vector bundles, etc. And the maps are, of course, just the maps like this. So this triangle is commutative. So pullbacks are products in the slice category. And the next remark that if you have a terminal object, T is a terminal object, and if you take a product over the terminal object, what do you think you will get? Yep. Very simple exercise. Check this. And let's not waste time on this. So exam. One more remark. So we can generalize pullbacks to any sets of maps. So xi, fi, and this is mapped to some fixed object z. Well, this of course immediately also follows from the remark 2. Examples. Let's start with the sets. So what's a pullback for 3 sets and 2 maps? Say that. Again, I guess that's not a hard exercise. If you take this set, plug in into this diagram, and if you get a map T, this T1 and T2 actually, well, you'll get a map U that maps to this to that set. What if we look at some special cases? So what if I have some map F? I used G before, but okay. And here, this is just the second map is the inclusion of some point into Z. So what's the pullback in this case? Yeah, so this is a fiber of the map F over this point. That's an example of a pullback. Of course, we can generalize this and include not just point, but any subset. It will be preimage of this subset under map F. Well, there we can do special case. For example, X is a subset. This is little z. Little z is a point in the large z. So it's supposed to be large z. And that's a point. Yeah. So that's exactly what you call fiber in the first semester of analysis in algebra. Fiber of the map F over this point z. This is just a special case of this observation. Now let's embed two subsets. What's the pullback in this situation? So intersection is a special case of a pullback, and this allows you to give a definition of intersection in any category. In any category, start with an object, consider two sub-objects, and then take a pullback for the two inclusions. So that would, by definition, the intersection of sub-objects. It exists, of course. Yeah, so these are two inclusions, yes. Yeah, we're still in the first example sets. Yeah, so in general, in any category, I guess you could take as a definition of a sub-object an object plus a monomorphism. Okay, next example, still in sets. I want to take a map F and consider a pullback of a map along the same map. So what we have here. No, not exactly X. That's a question for the first semester. For first semester, if you have what it is. No, this is called the equivalence relation defined by the map F. Right? By applying this formula to this special case. This all the pairs such that F on the first element coincides with the F on the second element. So this will be some equivalence relation. You can check this. Diagonal is there, it is symmetric, it is transitive. And if you take a quotient by this equivalence relation, what you'll get? Not necessarily. No, this is just the set of equivalence classes for the equivalence relation. Yeah, on X. Equivalence relation is a subset on X cross X. This is binary relation with some special properties. You can take all the equivalence classes. Well, sometimes people write this, and if you want to specifically write what equivalence relation you use, you can write this. And it's kind of the version of the first isomorphism theorem for sets. So 2. This is all about sets. We're still in the category sets. This is the first example. This is just equivalence classes of the equivalence relation. Sure. Well, let's try to work this out. What if you take monoids and try to do the same thing? Let me use X and Y again for monoids now. Clearly everything works, right? So the only problem is you don't want to get just an equivalence relation here, right? It's just not enough. You probably want to get the congruence relation. Congruence. Yeah. So for congruence, what's a congruence? That is an equivalence relation with additional property that, for example, here on monoids you have product. If you have two elements, so say x is congruent to the x prime, y is congruent to the y prime, you can take products. So equivalence relation, but also respects the additional algebraic structure. Sure, and that's exactly the definition of a quotient monoid. Well, that depends what's your starting point. You can start with a monoid, then you take a congruence relation, which is an equivalence relation with this property. Then you can define a quotient monoid. Or you can start already with a monoid and the map, right? Then from this monoid and the map, you can construct this congruence relation, and then of course the first isomorphism theorem is still true as before. So here this is just an example in monoids. So in monoids we have one binary operation, and I just require that I have an equivalence relation that agrees nicely with this binary operation, namely that if all elements are equivalent, then where? You can say this in sets, that equivalence relations are such diagrams. But in monoids, you need to say that congruence relations are such diagrams. Well, you can try to do this, sure. You can try to take any category, any map. So this is F and F. If in your category there are pullbacks, right? You can define this object just by use this as a definition. But then there is a question why this will be true. No, we need an existence of this. This would be the first step. But then you want to recover, say, image of y by using this data. And this actually will need an additional requirement that you have these two objects, you have this third object, two maps, and this kind of dual universal construction, the co-limit. This is called the push-out. And then this square will be a pull-back push-out square. So then there is a notion of quotient. And there is a notion of congruence on the category. But also it's interesting to notice that if you go with the category of groups, right, the same works. You can still define an equivalence relation on a group. So let this be x, y, x. And then you can introduce the notion of a quotient group by a congruence relation, and you'll get image of F. It's the first isomorphism theory. The question is how this is related to what you do in the first semester with the normal subgroups. What are normal subgroups in this picture? The relations are exactly this congruence relation. What's a normal group from the point of view of this congruence relation? Yeah, we can define the following thing. We can take all elements H, say in the X, such that 1H is in the equivalence relation. And that's a normal subgroup which we usually call the kernel. Normal in the X. And we can go in the other direction. So if I have H which is normal in the X, I can define the corresponding congruence relation. Now this will be just all pairs, say G, G prime. And what would be the condition? Formula you all very well know from the first semester. Normal. Now, this is just notation for the normal subgroup. No, that's all you need. That's exactly how you define an equivalence relation when you study left to right cosets. So an equivalence relation generated by the normal subgroup. So the point is that if you work in any category, it's kind of not very clear how this is related to a quotient by a sub-object. Well, we have very special sub-objects like normal subgroups in the category of groups. We have ideals in the categories of rings. But in general, the general language all is just give us congruence relations. And this is how you're supposed to work in more general algebraic categories. For example, in monoids, there is no notion of a normal submonoid. It doesn't make any sense. There's only notion of congruence relation. If you take, for example, semi-rings, again, there is no notion of an ideal. You only have congruence relations. In semi-rings, you have everything as in rings, but there is no minus x. So there is no inverse, additive inverses for the elements. For example, like in natural numbers. That's a semi-ring, not a ring. Okay. Now you saw a lot of examples, so it's time to give you a general definition. So limits of functors. Definition: a limit of functor z. Oh, I want to call functor d because this stands for the diagram, and I don't want to underline this category I. That would be an exception. So what's the limit of a functor? Well, is, as was predicted, a terminal object in the comma category, delta d. Okay. We need to understand, of course, what we have here. What's delta? Yeah, so we have a category C. We have functor delta to the category of functors, and the second functor is just induced by the object D, which is just an object in this category. So delta is the following functor. Delta takes object C and sends this to the functor delta C. And this is constant functor. We call that the constant functor has the following property, that if you want to compute this on some object I, and this is C for any I. And of course, for any map, this is just identity. Okay. To the functor D. Yeah. Yeah. To the functor, which is just a constant functor with this object. Yeah, so the correct formula will be delta of C is delta sub C. Delta sub C is a constant functor, and this is the definition of a constant functor. On any object, this is the object C, the same for OI, and for any map, this is identity on this object C. Okay, now we still, well, that's a delta. What's object in this comma category? So if you just go back to the previous lecture and look at the definition of a comma category, this will be the following. You'll get functor delta C for some object C, and then a map, a natural transformation P to the functor D. That's an object in this comma category, by definition of a comma category. So D is fixed, C and P are varying. Okay, what it means in more naive terms? So it means that from the object C, I have maps projections Pi to the D of I. And if I have two projections, say, and I have also Pj to the D of J, then I have a commutative triangle. And this is for any map U from I to J. I just rewrote what it means to have a natural transformation. Notice that kind of the usual commutative square collapses to a triangle because this is a constant functor. So answer for any object is just C. So I'm going to get C, identity, and C. So I just collapse this to one object. And that looks a lot like we saw before, right? We introduced some auxiliary categories, studied terminal objects, and that was interesting objects. So here, the category is exactly this category. So this is why the terminal object is called a limit. So what else I can? Oh, maybe I can draw this as a picture. Maybe it will be easier to understand. Okay, when you study limits, you kind of have three data. You have I, C, and D. I give you the shape of your diagram. Like for example, for products, for binary products, I is just 2 points. Right? For pullbacks, the form of I is just 3 objects and 2 maps. So you can say that, well, you have something like shape, where you have objects, some arrows, maybe something else, maybe it's a huge diagram. So this is kind of dictated by the indexing category I. Now, if you want to apply to this indexing category functor D, well, we get some specific objects like X, Y, Z, F, G, H. This is the result of application of the functor D. Now, that pair delta C and P means that I have some vertex C, and from this C I have projection. These are projection maps, say this is P1, P2, P3. And for all these projections, whenever it makes sense to consider a triangle, for example here, this is a triangle, this triangle has to be a commutative triangle. That's the last condition on the previous whiteboard. That's the limit. So, some diagram. Well, from this abstract definition, they come as a components of this natural transformation. From what we saw in our examples, a limit was always an object and projections to these objects to the diagram. don't quite understand the question. If you start with this abstract definition, you know what are projections because in the comma category, objects are C and P, pairs, C and P. And P is just natural transformation, such that component-wise I can write this as these projections to all the objects. So this could be just another definition of a limit. If you don't like this very short and concise definition, well, look at this like this. I give you a diagram, and for this diagram, you kind of want to find this cone with the vertex C. And this is a terminal object, so it has a universal property, meaning that if I have some other testing vertex, say T, I have some other projections, say Q1, Q2, Q3, there is a unique map here, U. So as before, there is kind of fixed part of the diagram, there is a cone over this diagram, and there is a universality property for the cones. Another way to say this that the limit is a terminal object in the category cones over diagrams of a given shape. Okay, how much time I have left? 20? I think I'll have like 10. 10? Okay, then I think I can prove main theorem today. But before this, I want to give one little remark. Notation. Notation and terminology. So notation for this terminal object is lim ID. This is one possible notation. There are many other possible notations. For example, people use lim and draw this arrow, this inverse limit going in that direction. It doesn't make sense at the moment. It will make sense next week when we discuss some examples. And sometimes even people write something like lim I in the I, d of I. It's also sometimes in some formulas it's useful to use this index to see what index you're using to get the correct formula. My personal favorite notation is the following. I'm writing limit D as an object, and then I write projections, and then parameterize everything by the I. So it's a little bit longer than just this short formula, but you can see everything. What's an object? Well, usually you don't write lim like this. You write a specific object, and you somehow want to define the specific projections, and this is usually given as part of a problem. So this is equivalent in the short notation to the following formula: delta sub lim D mapped by P to the functor D. Okay. Remark, maybe notations and remarks, maybe a separate point anyway. So the limit, if you fix diagram I, you can consider this as a functor from the category of functors back to C. Right? Take a functor, compute its limit, it's an object in C, that's the result of application functor limit I. Well, this is a functor. For objects, we know what to do, right? Object is a functor, compute limit, it's an object. Of course, this works if we assume that there are limits for all functors of a given shape. So if it exists, then this is a functor. No, from the category of functors, so D lives here, and D is mapped to the limit. Unique after a unique isomorphism, as usual. Well, sure. Skeleton of C. Yeah, but what I want to... Yeah, if you fix kind of how you choose this limit in some consistent way. Sure, but you need to, but you need to choose for a, well, I is fixed. If when for any d, you need to a way to choose the canonical construction for this, right? If you want to compute this, well, imagine some diagram, right? So whenever you put some objects x, y, and f in the diagram, you need to say what for this particular diagram, how you choose a special answer for this limit. You need to know how to do this consistently for all diagrams. Yeah, I think this works, yes. Okay, maybe I just can remove skeleton. Anyway, so there is still a problem. So far, it's only defined on objects. We need to define this also on maps. And then this will be a functor. And I'm going to leave again as a usual exercise that this is perhaps compositions to compositions. So what we need to check? Well, we have a natural transformation, alpha, between two functors. Well, then I have, so this is the place where it's convenient to use this short notation. So I have this natural transformation. I can do the same for the second diagram E. So let's maybe call this Q. Maybe I don't need the name for this. So, and alpha. Right? What was delta? This is P and Q. This same thing. This is a constant functor with this object. So as before, we were writing the diagrams like this. Right? That was an object in the comma category. Now I just choose C to be not just any vertex of any cone, but I want this to be a terminal cone. So the vertex is called limit by definition. So we have this diagram, and if I want to say this is a functor, I want to say that there is a unique map making this square commutative. Yeah. By definition, since this is the terminal object, and this composition is a natural transformation. Category of cones. So you can see the category of cones. Well, this is the terminal object, and this object with this composition give you another cone over the same P. Hence, by the terminality, we get this unique map. And we can call this. We can also give this map a name. We can call this lim alpha. I think it's more or less clear from this diagram that maps compositions to compositions, identity to the identity. Another little thing for you to check, that you have the following natural isomorphism, or natural bijection of sets in this case. Lim alpha is nothing, it doesn't make any sense, because since alpha is natural transformation between two functors. So we define this to be this map here. So this is limit of a functor, this is limit of a functor, and there is a map between these two functors. Of course, this means that we also have a map So that's the thing that we discussed when we discussed products. That was a bijection which is obtained by composition with projections. Of course, we can do this for any diagram, not only for products. And if you just look at this, what you notice that the limit is a right adjoint to the diagonal functor. That's another short definition of a limit, right adjoint to the diagonal. And this also coincides with what we discussed, I think, on the previous lecture, when we discussed right adjoints as initial objects in some categories. No, this means exactly this. It's the same thing. Here? This is in the functors, yes. Well, you have an object here, right? What's an object here? This is a map. Right? In other words, this is a cone over D. Sure. But then there is a unique map since limit is terminal. Maybe let's call this some Q, and this is canonical projections. Limit. Yeah. So this gives you a map from C to the limit D. This map. And if you have a map here, this gives you a map here. You just take composition with canonical projections, and you get this natural transformation element from here. Okay, examples. I is an empty set. So what's the answer for the limit? Yeah, terminal object in C. I is just a set with 2 points. So what's the answer? Okay. I is a set. Well, I guess you see what's going on. I is this is equalizer, and if you consider this diagram, this is pullback. So what we've discussed so far is special kinds of limits for these special diagrams. Of course, you can consider other diagrams. You can draw any diagram you want, but the point of the next theorem is that actually there is no point in doing this, because essentially there are only 2 limits. So theorem suppose category C has equalizers for pairs, of course I mean for all pairs, and all products indexed by objects of I, so I is fixed, and arrows of I. Then for any diagram D, which is a functor from the index in category I to the category C, there is a limit ID. So to show that there is any limit, you actually need to only very special kinds of limits. Only products and equalizers are enough to construct any limit you can imagine for any possible diagram. And the proof of this theorem is not very hard. Let me just introduce some notation for shortness. Let me call I0 all objects in the category I. Objects are just arrows. No. Object in this category is just any. So I want to consider this just as a set of all possible arrows, and I don't fix x and y. that's true, then this theorem doesn't tell you much. So, well, that depends on how you want to do things. If you want to allow products which are not parameterized by sets, then this is still meaningful theorem. But if you only want to consider the so-called small limits, meaning that I is a small category, right? And this is still not enough. Wait. Well, if this is a small category, then this is a set. So anyway, if you have enough products, then you have all the limits. That's the point. For example, you can formulate this for a finite. Suppose you're interested in all finite limits. Then it's enough to have equalizers for pairs and all finite products. Well, what's an equalizer? You have two maps between the objects, and the equalizer is just an object in a map. Yes. For any f and g, if I think about arrow, I suppose that x and y I can compute by this arrow. X is domain and y is codomain, so it's kind of given. So for any f and g, there is an equalizer. Okay. So I want to consider the following product. I take the product over all objects. So I is in I0. Then I take product over all arrows. So u is from I to j. And then for the u, I put d of j here. So these two products I have by the assumption. Right? What? Yeah, just a set of all objects. The point is that you have short notation here in this product. That's all. Okay, there are two maps here, phi and psi. If I want to define a map to the product, it's enough to define this for the components, right? If I know map phi, it's the same thing as knowing composition of the phi with any projection here. So this makes the following definition meaningful. Composition pu and phi is the same as ej, and the composition of the projection pu and the map psi is d of u pi. That's the definition of phi and psi. Oh, here we have canonical projections. Projections are pu, but for any product we have canonical projections. D of j. But because this works. Well, I want an object here, right? If I write d of u, this will be a map. And I want an object in the category because I want to know how to compute products of objects in the category. No, everything that I've written here is correct. I have a map u from I to j, and here I put d of j, the target of the map u. Well, let me say it like this. For a product, I have projection pu, right? For any index in this set, I have a projection. So this projection will be to the corresponding object parameterized by this u. The corresponding object is d of j. So the projection will be to the d of j. Right? So this is pu. Now, if I take a composition phi with a projection, this will be a map from this product to the dj. I just require this to be exactly the same thing as a projection from this product to the dj, which is given. This is a product. So that's the first formula. And the second formula is almost the same, but I kind of recompose it with du. So there are such maps phi and psi given by these projections. Now, yeah, this is product over all objects, and this is product over all maps, or all arrows. And we know that there is an existence for both products. No, it exists because I gave you components. Components are Pj. Any map to the product is uniquely determined by its components. So here I gave you components for the first map and for the second map. Yeah, so with these two formulas, I can define phi and psi. They exist uniquely. Okay. What if I have other object t and a map little t to these two objects, or kind of want to construct a fork diagram? And t, of course, I want to equalize phi and psi. So condition is phi t is equal to the psi t. So I'm studying category of cones for this diagram. And that's my condition. Of course, notice, by the way, that when you study equalizers, the cone will be an object, and you're supposed to have map from this object to here and to here, such that all the triangles commutative. But this information is redundant because it's not enough to have only one map here, because the maps here are just these compositions. So I don't need to draw any additional projections because they are automatically given. So I want to understand this condition. Phi t is equal to the psi t. Well, let's apply projections to this formula. Well, I have pu phi t is equal to the pu psi t. Now, this is the same as pj t is equal to the what? D of u e I t. Right? I just started with equalizing condition, write in terms of components, use previous formula which I was using as a definition of phi and psi. That's the formula. Okay, does it remind you something? So T, which is equating these two maps, is exactly as a cone over original diagram D. Yeah, so this will be the projections. So we can write this in the following sense. T with the maps which are EI T, little t, to the DI. So this is a cone, or what we call it an object in the comma category. Because this is exactly the condition we have for cones. Right? For any triangle that is possible to draw, this triangle has to be commutative. Right? So we have two objects I and J in the diagram. The arrow between them is U, right? So U is from I to J, and this is commutativity of the corresponding triangle. That's all. We prove this theorem. We see exactly that cones over this diagram is exactly the same thing as the cones over the original diagram D. Hence, the diagram, the categories are at least equivalent. Hence, they have the same terminal isomorphic terminal objects. Existence of a terminal object in one category is equivalent to existence of a terminal object in the other category. That's the end of the proof. And the end of today's lecture. Because we actually see that the categories are kind of the same. again, we form this category, this part of the fork, and study cones over this category. That's a object T with this one projection T. We rewrite this a little bit, and we see that this is equivalent to this condition. And this condition is exactly the condition that we have a cone with vertex T and such projections over the original diagram T. Yeah, so we can start with little t and condition that the little t is equalizing, get this condition. We can start with this condition, which is condition for the cone. All the formulas are equivalent here. So go from here to here and to here, and we see that this is kind of cone over this diagram. So the category of cones are the same, hence existence of the terminal object in one category is the same as existence in the other category, and these two objects are isomorphic. Там была задача про липшицевые эти самые. Кому-то еще хочется задать? Была задача